Today, we shall study about the standing waves and normal modes. Let us consider a system which is bounded at both the ends, such as the stem fixed at the ends, or a column of finite length. In such a system, suppose that we send a continuous sinusoidal wave of a certain frequency. The process will continue, and very soon we have many overlapping waves which interfere with one another in such a system at any point x and at any point t. There are always two waves, one moving to the left and another moving to the right. We therefore have by one xt power a sin k minus omega t, wave travelling in the positive direction of x-axis, and by 2 xt power a sin kx plus omega t, waves travelling in the negative direction of x-axis. The principle of superposition gives for the combined wave by xt power by 1 xt plus by 2 xt power a sin kx minus omega t plus a sin kx plus omega t power 2a sin kx omega t. That is equation number 1. The wave represented by equation 1 does not describe a wave as a wave form. The disturbance does not move either side. In the travelling wave, the amplitude of the wave is same for all elements. Equation 1 represents a standing wave, a wave in which the waveform does not move. The amplitude is 0 for values of kx, that gives sin kx power 0. These values are given by kx power n pi for n power 0, 1, 2, 3, dash dash, substituting k power 2 pi by lambda. In this equation we get x power n lambda by 2 for n power 0, 1, 2, 3, dash dash. The position of zero amplitude is called nodes. The amplitude has a maximum values of 2. The amplitude has a maximum value of 2a which occurs for values of kx, that gives sin kx, mod sin kx power 1. Those values are x kx power n plus 1 by 2 into pi. Substituting k power 2 pi by lambda, we get x power n plus 1 by 2 into lambda by 2 as the position of maximum amplitude. These are called the antinodes. If it is separated by lambda by 2 and located halfway between pair of nodes, the frequencies corresponding to these wavelengths follow from up v power nu lambda from equation v power nu lambda as v power n nu power n v by 2l for n power 1, 2, 3, where v is the speed of travelling waves on the string. The set of frequencies given by equation 1 are called the natural frequency. These are modes of oscillation of the system. Now, this equation tells us that the natural frequencies of a string are integral multiple of lowest frequency. Nu power v by 2l, which corresponds to n power 1. The oscillation mode with that lowest frequency is called the fundamental mode or the first harmonic. The second harmonic is the oscillation mode with n power 2. The third harmonic corresponds to n power 3, and so on. The collection of all possible modes is called the harmonic series, and n is called the harmonic number. Some of the normal modes in an air column with the open in are shown in figure. The fundamental frequency is v by 4l, and the higher frequency are odd harmonics of the fundamental frequency 3v by 4l, 5v by 4l, etc. In the case of a pipe open at both ends, there will be antinodes at both ends, and all harmonics will be generated as shown in the figure. Now beats the phenomenon of wavering of sound intensity when the two waves of nearly same frequency and amplitude travelling in the same direction are superimposed on each other is called beats. Musicians use the beat phenomena in tuning their instrument. If an instrument is sounded against a standard frequency and tuned until the beat disappears, then the instrument is in tune with that standard frequency. Now, Doppler effect. When we approach a stationary source of sound with high speed, the pitch of the sound heard appears to be higher than that of the source. The observer, the observer, the observed pitch or frequency becomes lower than that of the source. This motion related frequency change is called Doppler effect. So it is a wave phenomena. It holds both for sound waves and electromagnetic waves. We will study for sound waves. We analyze changes in frequency under the stress under three different situations. When the observer is stationary but the source is moving, second observer is moving but the source is stationary, third both the observer and the source are moving. Now first, source moving and observer are stationary. As shown in the figure, observer is stable and source is moving from S1 to S2 position. The length between observer and source is L, so L barabar VST0. The distance between the observer and the first source position. Now figure A, source moving with velocity Vs emits a wave crest at the point S1. It emits the next wave crest at S2 after moving a distance Vst0. Now we consider a source as moving with velocity Vs and an observer who is stationary in a frame and an observer who is stationary in a frame. Let the speed of the wave of a angular frequency omega and the period to t0 both measured by an observer at that with respect to medium. But we assume that the observer has a detector that counts everyone a wave crest. So T1 barabar L by V at T barabar T0. Now T2 barabar T0 plus L plus V to V S T0 by V. Now T plus N plus 1 barabar N T0 plus L plus N V ST0 by V. So T barabar N T0 plus L plus N V ST0 by V minus L by V bata N बराबर T0 plus V1 T0 by V बराबर T0 into 1 plus Vs by V. इसलिए न्यू बराबर न्यू बराबर Vs into 1 plus Vs by V to the power minus 1. इसलिए न्यू बराबर न्यू 0 into 1 minus Vs by V binomial series. For a source approaching observer, न्यू बराबर न्यू 0 into 1 plus Vs by V. That is the case number 1. Now observer moving, source stationary. Observer moving with velocity Vs. The time interval between the arrival of the first T and Tn plus 1 is Tn plus 1 minus T1 बराबर Nt0 minus N Vst0 बटा V0 plus V and T0 into 1 minus V0 बटा Nt V0 plus Vs बराबर T minus 1 plus बराबर 1 plus Vs by V to the power minus 1. इसलिए न्यू बराबर V0 into 1 plus Vs by V. That is question number 2.